Let's jump right in. Today, we're exploring one of the absolute most mind-bending mysteries in the entire cosmos, the unimaginably extreme remnants left behind when massive stars explode. We're going to see how scientists are basically using a cosmic sonogram to listen to the core of dead stars and figure out states of matter that literally exist nowhere else in the modern universe.
So it all starts with one fundamental question. What actually happens when a star dies? Well, when a star that's, say, 8 to 20 times the mass of our Sun finally reaches the end of its life, it goes out with a massive bang, a supernova. The outer layers get blown away, but the core? It collapses under its own immense gravity. It violently squeezes down, crushing what used to be the burning heart of a giant star into a tiny sphere no bigger than a small city. We're talking just 20 kilometers across. And that is what we call a neutron star.
To even begin to grasp the sheer scale of what that collapse creates, you have to consider this number: 400 million tons. That is the staggeringly incomprehensible mass of just a single cubic centimeter of neutron star stuff, sometimes called neutronium. I mean, if you were to somehow scoop up that tiny cube and set it on the ground right here on Earth, it would be so intensely heavy that it would literally just fall right through the planet. To really wrap our heads around this kind of density, imagine taking 200 million cars, which is roughly every single vehicle in the United States, and crushing them down until they all fit inside a standard six-sided die. Crazy, right? How is that even possible? Well, normal matter, like the atoms making up your body, is actually almost entirely empty space. But in a neutron star, the gravity is so extreme that protons and electrons get violently smashed together to form neutrons. And every single bit of that normally empty atomic space, it gets completely packed with neutrons, no empty room left at all.
Section 1. Journey into the core, 100 billion G descent.
Okay, so imagine you could somehow stand on the surface of one of these beasts. First off, you'd experience a gravitational pull 100 billion times stronger than Earth's. But look at what's beneath us as we descend. Your head would be out in the vacuum of space, sure, but your feet would be standing in a 10-centimeter thick atmosphere of incredibly hot plasma. And right beneath that foggy plasma is a solid crust. Actually, it's a frozen plasma where iron nuclei, completely stripped of their electrons, are locked together in a super stiff crystalline lattice by these insane pressures.
Stepping down through this structure, we essentially pass through three main zones. First, that iron lattice outer crust we just mentioned. As we tunnel deeper, the pressure gets so unimaginable that the nuclei actually become overloaded with neutrons. We hit this bizarre phase known as neutron drip, where neutrons are literally leaking out of their nuclei into the shrinking space between them. Go even further down, right into the core, and you'd find a frictionless, superfluid ocean of neutrons. But right above that core, well, that's where things get genuinely weird.
Section 2. The nuclear pasta phase. Extreme matter.
As we drop about a kilometer down from the surface, the density jumps to 1,000,000 times greater than what we saw on top. 1,000,000 times! We are now dealing with forces that completely rearrange the structure of matter itself. Physicists affectionately call this phase nuclear pasta. And yes, that is a very real, actual scientific concept. At these ridiculous densities, particles are playing an extreme game of quantum tug-of-war. The nuclei radically reform into long cylinders filled with millions of protons and neutrons. That's your nuclear spaghetti. Squeeze it just a little bit more and it flattens out into sheets. Nuclear lasagna.
Now, compared to normal steel, this nuclear pasta is estimated to be a quintillion times stronger. Think about that. It might actually be the single strongest material in the entire universe. And because it is so unimaginably rigid and dense, it can resist the star's insane gravitational pull just enough to support tiny mountains buried beneath the surface. When I say mountains, I'm talking about these jumbled textures that are maybe 10 centimeters tall. But don't let the size fool you. Every cubic centimeter of that 10-centimeter mountain weighs as much as an entire mountain range here on Earth.
Section 3. Ripples in space-time. Hearing the unseen.
Which brings us to a massive scientific roadblock. Because everything we just discussed about the inner crust, the pasta, the superfluid core, it's all highly theoretical. We obviously can't physically fly out and drill into a neutron star, so how on earth do we prove what's actually inside them? Well, a recent study by Luz, Scott, and Whitney lays out the problem perfectly, stating that what exactly neutron stars are made of is an open question, and that just a few kilometers below the surface, the density is expected to exceed normal atomic nuclei. Terrestrial experiments just cannot recreate these crazy densities, meaning the internal equation of state, the exact physics describing how matter behaves under this kind of pressure, is still a massive mystery.
We basically need a totally different messenger to bring us this information.
And here is where the brilliant breakthrough comes in. It all goes back to those tiny, ultra-dense 10-centimeter nuclear pasta mountains. See, neutron stars spin incredibly fast. We're talking sometimes hundreds of times a second. So as those incredibly dense little mountains get dragged around in rapid circles, they're constantly churning the very fabric of space around them, radiating ripples that we call gravitational waves.
Section 4. Hearing the continuous hum. A cosmic sonogram.
Now, when two neutron stars actually collide with each other, they create this massive, violent chirp in gravitational waves. But an isolated, spinning neutron star with a bunky crust, it does something totally different. It creates a persistent, continuous hum that rings out at exactly twice the star's rotation frequency. It acts exactly like a cosmic sonogram. And observatories like LIGO, which measure the incredibly tiny stretching and squeezing of spacetime using lasers, are actively searching for this ultra-weak, continuous signal right now to reveal the physics buried inside.
So, what's the payoff? What happens once we actually detect this continuous hum? Well, by analyzing this sonogram, we can extract 3 incredible secrets about the star's interior. First, we get the moment of inertia, which tells us the overall mass distribution, basically how all that crazy matter is physically arranged inside. Second, we find the ellipticity, which gives us the exact size and shape of those asymmetric nuclear pasta mountains. And third, the magnetic moment, which reveals the strength of the star's internal magnetic field. We are literally figuring out how to map the physics of the star's inside by listening to its gravity.
But unlocking those 3 secrets isn't quite that simple. It requires some serious cosmic detective work. We can't rely on gravity alone. We actually have to combine it with light-based telescope data. We track the star's electromagnetic parallax to pinpoint its exact distance from Earth. We also measure its breaking index to see how much energy it's losing to light versus gravity. And once we combine that light data with the continuous hum of the gravitational waves, the star's internal code is completely cracked.
And that leaves us with a truly thrilling thought to wrap up this explainer. Think about it. If a 10-centimeter bump of nuclear pasta can literally sing to us across the galaxy by plucking the strings of space-time, what else is out there? What other exotic states of matter might be hiding in the dark universe, just waiting to be heard? Listening to gravity isn't just a fun new way to observe the stars. It's the ultimate tool for unlocking the most extreme physics in the universe. Keep your ears to the cosmos.